Hello my dear students, this is Akash SD and welcome to the ASD physics classes. So students, I hope so regularly you are watching the videos of the gravitation now. So in today's class we are going to learn about the cases of the gravitational potential due to different bodies. Okay, so let's start the video and let's start learning. So students, as I told you, gravitational potential of different bodies, graphs of this topic is the very important, is it? So see here please, what is the first topic here? The gravitational potential due to hollow sphere or a spherical shell. So see here please, here let mass and radius of hollow sphere is m and r respectively. So first we are going to calculate gravitational potential outside, then we will calculate at the surface, and after that we will calculate inside also. So let's start one by one. So first what I have taken here, first I have taken here one point A, okay, and let's take the radius of this shell is capital R, and the center to the observation point distance I have taken small r. So if I talk about outside, so here what will happen that here small r is smaller greater than r. So what happens that whenever the observation point is outside, the total mass of the sphere can be concentrated at its center, and in this situation we have to just write the formula of gravitational potential due to the point mass, formula minus gm by r, very simple. After that, similarly, if we talk about at surface means where? At surface means always just outside. So here what I have done, students, here I have taken one more point here. Let's take now my point is here point B, where? At surface here. Now center to observation point small r. So here what will happen, small r will be equal to capital R. In this situation also, as the point is just outside, total mass of the sphere can be concentrated where? At the center, and again we have to use the formula of the point mass minus gm by capital R. Now the main thing arises when we are going to calculate the potential inside. So when we will take the potential inside, so inside again what will do here? Here I have taken some more point C, and now let's take this distance is r. Okay, so in this situation we can tell small r is less than r. Very important, listen kindly very carefully. So what happens that in this situation we have to use the relation between gravitational field intensity and gravitational potential, and in last video I have taught that this is given by dv equal to minus I dr. Okay, so here what will happen that here through the point C I will draw here one imaginary sphere, is it? So you know very well the total mass is present on the surface. Is there any mass inside? There is no mass inside. Inside mass is 0. There is no mass. So as there is no mass, what will happen? The gravitational field intensity inside will be how much? 0. Is it? So because of that we can write here this term will become here 0, because I value how much? 0. And please remember that we have to put the limits also here. Here we'll write here when small r equal to capital R, here which potential? Surface potential. And when we are inside, that means how much distance is small r, and here what is there? Normal potential, what? V. So when we'll do here, students, upper limit V minus lower limit Vs equal to 0. So from here what will happen that here V equal to Vs, or this is the which point? Inner point. That means we are understanding what? Whatever potential at the surface of the shell, the same potential will be inside also. So just for the example, if I take here one hollow sphere like this, hollow sphere, and if I take some point A, B, C, D, generally I have taken, so what will happen? Potential at all the points will be same. There is no potential difference. So as there is no potential difference, that's why what is there? That's why only this GFI inside the shell is 0. Please remember that. Okay. So after that we are going to see gravitational potential of the concentric shells, and here we have to use the concept of the whatever we have learned for the shell, because this is very important for the 12th point of view. There concentric shells will be there with the charges. So see here please, here I have taken like this. This is 1 and this is 1. Okay, and let's take students here I have taken this one is having mass m1, this is mass m2, this radius r1, and this radius r2. Okay, so now let me draw here. First I will take one point here. I have taken point A, and this distance how much? This distance is r. Okay, so students, first one, potential at point A will be what? Due to first shell, this is the first shell, this is the second shell. So we'll write here VA with respect to 1 plus VA with respect to 2, and say here A with respect to 1 outside, A with respect to 2 also outside. That means total mass can be concentrated where? At the center, at the center. That means what formula will become here? Minus G M1 by R, center to observation point, na, R, minus G M2 by R. This is the total potential at point A. After that, students, if I take one more point here, let's take, I have taken one point B here somewhere. Okay, again center to observation point R. So now, students, in the second situation, see, potential at point B is given by B with respect to 1 plus B with respect to 2. Now think please, B with respect to 1, this is the 1, so which side? Outside. Outside means always actual length, but B with respect to 2 is where? Inside. And whenever this is the inside, you have to take which potential? You have to take the surface potential. So outside means, see please, minus G M1 by actual distance R minus G M2. Inside means surface potential. What is the surface potential for the second one? Minus G M2 by R2. So this will happen that here. Is it? Similarly, if directly I'll tell for this also, I have taken one point C here. Now I will write directly. Let's see how many of you will understand this. This VC will be VC1. So VC1 will be how much here? Tell me please here. This is inside. That means minus G M1 by R1. VC2, that is also inside. We have to take the surface potential. That means minus G M2 by R2. Now, you are very intelligent. You can understand it very easily. We have to just remember that here, whatever potential at the surface, same potential will be inside also. Okay, students. Next one, we are going to see gravitational potential due to solid sphere, and we know Earth is also solid sphere. That means this concept will be applicable for the Earth also. Okay, so let's see one by one. Let mass and radius of solid sphere is m and r respectively. M and r respectively. This is the radius. Okay, so gravitational potential outside and at surface will be similar to the gravitational potential of the hollow sphere. Is it? So whenever it is coming in the same way, we have to write here. First one, if I am talking about the outside here, so here what was the formula was there? V out minus G M by R. Similarly on the surface, what was the formula was there? Surface means just outside, so it was Vs equal to minus Gm by capital R. The main situation arises inside. So when we'll see inside the solid sphere is there. Okay, so you know very well, if in case this is the solid sphere, that means what will be there? Inside mass is present now. Inside mass is present. So in this situation, what will happen? The potential will not be constant. Then what we have to do? We have to just see here please, this is the radius R, is it? And here I have taken some point small c, and this distance how much? This distance is small r. And after that, what we'll do, students, here we have to just draw one imaginary sphere here. Okay, so you know very well this I, what is the formula? The gravitational field intensity inside the solid sphere is always given by, if you remember, Gm into R by R cube. This is the inside there, is it? So this we have to use here. So you know very well, we know that the dV is equal to minus I dot dr. Okay, and here what we have to do, then we have to put the values now here. So here please, dV, and here minus I value how much? Gm into R by R cube into dr here. Now we'll consider that here potential and dr in a same direction here. Okay, now after that we have to put the limits, students. So here please, here when small r equal to capital R, where we are on the surface. Here we have to write the surface potential, and when we are at point C, then small r, and here which potential is there? Let's take potential is V in. So here it will become here V in minus Vs is here minus Gm by R cube integration of R dr. That means R square by 2. Limits where to where? Capital R to small r. You will simplify this, and Vs value you will put minus Gm by capital R, and after that, students, when you will write the value, so this Vn will come here. Remember that minus Gm by 2R cube. 3 capital R square minus small r square. This is the potential value inside the solid sphere. After that, one more concept is there. What is the concept? Sometimes they will ask at the center of the solid sphere here. Okay, so at the center of the solid sphere, what will happen, students? Here please, at the center value of small r, how much? 0. That means we can write here at the center v not equal to, put the value please, minus gm by 2r cube 3 capital R square minus small r square. Now here this smaller value is how much? This smaller value is the 0. That means it will come 3 by 2 minus gm by r. Is it? That means potential at the center is 1.5 times of the surface potential. Kindly remember it very well. So students, based upon that, if we draw the graph also here, graph, just let me draw the graph also here. So when we'll draw the graph now here, so see here please, here I have taken here like this. I have to draw the graph here, and here directly I will draw with the minus sign. I will not draw with the magnitude and all that. So here let's take this is small r. We know very well small r equal to capital R, and here small r equal to minus r here. Is it? So how the graph will look like, students? Here the graph will be, please remember that very well. This is the surface potential Vs, and here 1.5 Vs. Just draw me. Let's draw like this, and let me change the color. Is it? Very easy. So it will go like this here, and here also. Like this it will go here, a little bit here, little bit curved. Okay, so this is the potential value due to the solid sphere here. Is it? And this value how much here? This value 1.5 Vs, because potential at the center is how much? 1.5 times of the surface potential. Here Vs and here also Vs. Directly I have drawn with the minus sign, no magnitude and all that. Okay, maximum they will ask this only. Is it, students? So after that, what we have to do? Next one we have to, already we have completed this. No? So next one what we have to do now? We have to see gravitational potential on the axis of the circular ring. Is it? So what will happen that here? As usual, mass and radius of the circular ring is how much? M and R respectively. So see here, students, let's take this is x-axis, this is y-axis, and this is z-axis. And here I have taken one ring. Very easy. This derivation is going to be easy because potential is the scalar quantity in us only, and the radius of the ring is r. Okay, and after that, students, here we have one observation point P, and distance of the observation point from the center, from the origin, is how much? From the origin it is x. After that, students, what will happen that here? As the ring is the which kind of distribution? Continuous mass distribution. That means I will take here very small mass dm. Okay, and here let's take this distance is small r. So what I am writing here, see here please, gravitational potential dv at a distance x due to small mass dm of the ring is given by formula. So here please, here this dv is given by here minus g into dm by r. What is r? Mass to the observation point distance. Now after that, here hence gravitational potential due to ring is given by formula v equal to integration of dv. Put the values please. G and r is constant because each and every point mass of the ring has how much distance? Small r distance. That means minus g by r integration of dm. That means what will come? Minus gm by small r, because integration of the dm will be what? M. Is it? Now from the Pythagoras theorem, my intelligent, very intelligent students will tell me from the Pythagoras theorem, small r how much? R square plus x square. This is the potential at a distance x from the origin. After that, one more thing is there. If in case they ask at the center, sometimes they ask at the center of a ring. In a one case, at center of a ring. So students, at the center of the ring, when we are going to at the center of the ring, then value of x how much? The value of x will be 0. So as the value of the x will be 0, put here. So we'll get here at the center of the ring minus gm by r. Is it, students? So in this way, what we have done in this class, students, we have just calculated gravitational potential due to all the bodies, and especially the graphs are very, very important, and the concentric shell potentials also very important. Thank you so much, students, for watching my videos regularly.